Welcome. Last lecture. We're going to review for the final exam today. I am actually going to give you a little bit more time for the final exam than originally planned. Not that I'm planning on making it longer, but just to give you a little bit more time, because I know there are some people who definitely appreciate that. So we're going to start the exam next Thursday at 2:30 instead of 2:45. Final exam next Thursday. I'll give you 2.5 hours for it, 2:30 to 5. The ordinary start time is 2:45. Actually, the ordinary end time is 4:45, but we'll start 15 minutes early and go 15 minutes late. Again, not that I'm planning on definitely making it longer than I was originally planning. I just want to give you a little bit more time for it. You can use a whole sheet of paper, front and back, to write notes on. And you can use your calculator. You may need your calculator, so make sure you bring that. Today we will be reviewing. So I think what I said was I'm going to take old exam problems and take a sampling of them, modify the functions and numbers a bit, maybe the statement of the problem a bit, especially for true-false questions, and put those on your exam. Your midterm exams were typically 5 pages long, so I'm thinking this one might be maybe 7 pages. I'm not guaranteeing that, but that might be what it will end up being. So let's go ahead and look at the old exams and review what was on them. Think about the kinds of problems that we had, the kinds of methods that we had to solve them. Probably for sake of time, we're not going to have time to really go through many solutions. Maybe a few, maybe just hints, reminders about solutions, about how to go about doing them for sake of time. So we'll do that for exams 1, 2, and 3, and then at the end of class we'll review what we've done since the last exam, which is mostly the residues and the residue theorem and those applications to improper integrals. So here was exam 1. And again, I have to pick a sampling of these things, so not every problem on here will be on your exam. I have not started writing your exam yet, so I don't know what's going to be on it yet. I don't know which ones I'm going to pick. Before I start going through this, I should say, I think on each exam there was at least one proof. I think maybe on this first one there were a couple. I think there will be one proof on the final exam, and it will be similar to one of the old proofs. Just as a matter of way, getting that out of the way, so to speak. All right, do calculations and simplifying the following complex numbers exactly in rectangular form. This should seem pretty easy right now, I hope, looking at this one. Right, you divide two complex numbers in standard form, you'd want to multiply by the complex conjugate at the bottom, on the top and the bottom. You got to multiply by 1 to not change the quantity. So you multiply by 3 plus 7i on top and 3 plus 7i on the bottom, you simplify. What should you use there? What's it called? It's got a name. What do you use? Euler, yeah, Euler. E to the I theta. It's cosine theta plus I sine theta. That's what you're going to need there. And you should, you'll have a calculator, and that calculators these days can produce exact values of trig functions. But, if your calculator happens to not, you should know exact values of trig functions. Cosine of 4 pi over 3, what is that? 4 pi over 3, that would be what? 60 times 3, that would be 240 degrees. 180 plus another 60. The cosine is the first coordinate of the stopping point. It's going to be negative 1/2. What it would be. Sine of that would be negative square root of 3 over 2. Again, many calculators can do that exactly anyway these days. This one, there was a fast and easy way to do this one, but hardly anybody on that first exam, I think, when I was grading it, did it the fast and easy way. Most people went ahead and squared these out and divided. There's a faster and easier way. is to use properties of modulus. moduli, I should say, of the complex numbers. The modulus of a quotient is the quotient of the moduli. Like that. And the modulus of a product, for example, the modulus of a square of a complex number is the square of the modulus. You could write this. You're squaring moduli. You don't need square root symbols here. The square of the modulus of this is going to be 1 squared plus 1 squared. The square of the modulus of this is going to be 2 squared plus 1 squared, looking at the real and imaginary parts. So you're going to get 2 over 5 through those. Should be able to use that property in that kind of way. Identifying whether a set is open or not, connected or not, domain or not, bounded or not. Hopefully you've gotten used to this kind of set builder notation. This is the set of all complex numbers satisfying the property that the modulus is between the 0 and 4 strictly. Hopefully you can pretty quickly imagine such a set in your mind. This would be a punctured disk centered at 0 with radius 4. Is it open?
Yes.
Yes, it is. What does it mean for a set to be open? Point missing. The origin is missing from the set. What does it mean for a set to be an open set? That's harder. You could say all its points are blank points. Interior points, yep. Meaning, what does it mean to be an interior point? A point is an interior point of a set, whether that set is open or not, if there's some open disk centered at the point that's entirely inside the set. That's what it means to be an interior point, and a set is open if every point in the set is an interior point of the set. If you include the boundary, it's no longer open because the boundary points are not interior points. Take a boundary point, there's no open disk centered at the point that's contained entirely inside the set, no matter how small you make the disk. It's open, it's not closed. The only sets, two sets that are both open and closed are the empty set and the entire plane. This is neither of those. There are plenty of sets which are neither open nor closed. If I include, say, part of the boundary, but not the other part, then that's neither open nor closed. If I do include the boundary, that is a closed set. Its complement, the outside of the set, everything not in the set is open. The set complement of a closed set is open. The set complement of an open set is closed. Is it connected? It is, in spite of the fact that it's got a hole in it. It's not simply connected, but it is connected. We talked about connectedness in terms of what's called path connectedness. Given any 2 points in the set, you can connect them with some path, polygonal or not. It doesn't have to be polygonal like I drew it there. Made up of line segments. So that's connected, but not simply connected. But we're not talking about simple connectedness at the moment. Domain or not? Yep. In complex analysis, domain means open connected set. And everywhere else in math, domain just means domain of a function, the set of inputs. Oftentimes, a domain in the complex plane in complex analysis is the same as the domain of a function. But we use that in the special case of open connected sets. Is it bounded? Yep, doesn't go off to infinity. You can enclose it in some bigger disk. That's finite radius. The set is bounded if it can be, you can find some disk of some finite radius that contains the set. Here we have the z-squared function. Describe the image of the horizontal line described in this way. This would be a horizontal line at y equals 4 in the complex plane. The imaginary part is constant 4. In terms of an equation relating to u and v, and then graph this curve in the uv plane. Essentially, it's just a matter of plugging in your general point into the function. What is the nature of something like that? The real part is going to be x squared minus 4. The imaginary part, oh, excuse me, minus 16. Think about foiling it. The real part's going to come from first times first and last times last. And the imaginary part's going to come from outside and inside products, 4ix and another 4ix. It's going to be I times 8x. This is going to be u, this is going to be v. That's really a set of parametric equations in x instead of our typical parametric variable, which is t. U equals x squared minus 16, v equals 8x. You could use parametric mode in your calculator to graph it, but you'd have to use a t instead of an x. But you can also eliminate the parameter to relate u and v. And solve this one for x in terms of v. And then substitute that back up there, and what will happen is you'll get u is v over 8 squared minus 16 in a uv plane. That's giving us u as a function of v, a quadratic function. It's going to be a sideways parabola. When v is 0, u is negative 16. As v moves away from 0, u increases, so it's a sideways parabola, something like this. When you figure out the vertical intercepts, you set u equal to 0 and solve for v. You get v over 8 squared would have to be 16 at the vertical intercepts, and so v over 8 would be plus or minus 4. So v is plus or minus 32, it looks like, and I didn't really draw that accurately as far as the scale goes then. This evidently is 32, and this is negative 32. We're good? Let me know if you think I make a mistake. So that would be the image of this thing in the xy plane under z squared. You should think about it if it makes sense. 4i gets mapped to, under squaring, to negative 16. That makes sense. Points way over here. What happens? You're squaring, so the moduli, the modulus gets squared and the argument gets doubled. Points that are, say, way over here have a small argument, say maybe 10 degrees or something. The argument gets doubled to 20 degrees. They're going to get mapped to points that are over here on the parabola somewhere, where this angle would be double the original angle. And the distance, the modulus, should be squared. So if there was this picture, this would be a lot longer here. Parabolas don't have slant asymptotes. The angle, the argument of points on this graph does get arbitrarily small, so to speak. The further you go along that branch, there's no slant asymptotes or anything like that for parabolas. There are for hyperbolas, but not for parabolas. So it's making sense to me here. Points way over here are going to have a modulus or an argument close to pi. You double that, you're going to get close to 2 pi. They're going to get mapped to points. Mapped to points along this branch of the parabola. We spent the first half of the course, it seemed, on mappings. So we want to go back and think about mappings, functions as mappings. This one's pretty basic, at least part A. Plot and label these points. For the given point 3 plus 4i, so you need to understand what the symbols mean, the conjugate symbol, for example, and you can think geometrically. The conjugate symbol, the conjugate reflects across the horizontal real axis. A negative sign reflects through the origin. These points are going to form a rectangle centered at the origin. 1 over z is something different, though. In plotting 1 over z, you can certainly figure out what 1 over z is in terms of coordinates, but I think it would be good to remind you that you can also think of it this way. 1 over z is the same as z bar over z times z bar. And remember that z times z bar is the same as the squared modulus of z. That's good to remember. So you can think of taking a point z and mapping it to 1 over z as a two-step process, maybe even a three-step process. First, map it to its conjugate z bar. And let's pretend the unit circle is right here. Now divide z bar, say just by the modulus of z to begin with. That's going to go to a point on the unit circle, on this ray. Same ray through the starting at the origin. That's going to have a modulus of 1. Its modulus is 1, right? If you divide z by its modulus, it's like normalizing a vector, finding a unit vector in the same direction. The modulus of this it's not double absolute value signs like for vectors. But both of these equal the modulus of z. As long as z is not 0, this is 1. Anyway, so that's a point on the unit circle. Right there. It's not the final answer yet. Now divide by the modulus of z again. And with this picture, the modulus of z being bigger than 1, that's going to get mapped to a point inside the unit circle. The modulus of this point is the reciprocal of the modulus of the original point because it's equal to 1 over z. That's 1 over z. This is a set of points whose distance to 3 plus 4i equals 1. You see something like that, you should automatically think distance, z minus something. Now, of course, it could be given in disguised form. It could be given with a plus sign. Z plus 7 plus 2i. Well, let's make it minus 2i for an extra equal. What is the set of points that satisfy that equation? It's still a circle. Because you can rewrite this as the modulus of z minus, in parentheses, 7 plus 2i. Oh, negative 7, thanks. It's negative 7 plus 2i. So this is the circle of radius 3 centered at negative 7 plus 2i. So you should be able to deal with that kind of wrinkle. Oh, complex roots. We've forgotten this one. When you multiply a complex number by itself a certain number of times, say 3 times, its modulus, its distance to the origin, gets cubed, and its argument, its angle with the positive real axis, gets tripled. So if you go back the other way, and if you're thinking of just getting one answer, the principal value, say, of a cube root, you'd have to take the cube root of the modulus and you'd have to cut the argument down by a factor of 3, right? Divided by 3. Find all the complex cube roots of negative 64. It's helpful to write it in polar form. This is positive 64 times e to the I pi. So the principal cube root would be what you get when you take the cube root of 64, which is 4, for the modulus, and take the argument pi and divide it by 3. The other cube roots, which there's got to be 3 total. Every non-zero complex number has 3 cube roots. Other cube roots, you know, there's a formula in the book for these things, but I prefer just thinking about it. They got to have, the arguments between them have to be equal. They have to form an equilateral triangle centered at the origin. It might just be helpful to draw a picture. Pi root 3 is 60 degrees. So there's the principal cube root. You've got 2 other ones. The total angle from this principal one back to itself is 360. These other 2 ones have to be 120 degrees apart. Oh, one of them is negative 4. Well, you already knew that. Negative 4 is a cube root of negative 64. And before complex analysis, you would say that's the answer. Cube root of negative 64 is negative 4, you would have said before complex analysis. It's not the principal value, which brings me to another issue. I'm going to do something in mathematics here in a second. But it is the cube root you're more used to. And the other one would be the complex conjugate of this one down there. Negative 4 would be, in polar form, 4 e to the I pi. And this one would be 4 e to the I times either negative pi over 3, or you could also write it as 5 pi over 6. Either way is okay. Oh, no. 5 pi over 3, is that what I meant? Yeah, 5 pi over 3. What I meant. Yeah. So those are the other key roots. Should be able to write them in polar form. You should be able to transform back to rectangular form as well. Of course, that's just negative 4. Use Euler's formula for that one and this one. Would I give you a harder one than this? It's possible I might do a 5th root instead of a cube root. Plot it, find and graph all the 5th roots, write them in polar and rectangular form. What's this mathematic issue that I was hinting at? I think I talked about this the very first day or 2 of class. If you try to get Mathematica to, for example, calculate the cube root of negative 64, I think if I type it like this, it just spits it back to me as is, or modifies it a bit. But if I ask for that, the numerical approximation to that, it doesn't give me negative 4. It gives me the principal value. Mathematica is programmed to give you the principal value. If you want the real cube root of negative 64, you can use a built-in cube root function. That says negative 4. That gives you the real cube root. I think it was the very first day of class I talked about that. We were talking about Cardano's formula. Here we were taking z to the 4th and expanding it in real and imaginary parts, writing a formula for the corresponding real planar mapping, which Once you've done part A, part B is supposed to be easy. By the way, this notation, capital Phi, that I've been using for both the corresponding real planar mapping and the vector fields is not standard. In fact, I don't think I've ever seen another mathematician use it. But I don't know, I kind of like it. It's pretty. Whatever you find for U and V, for the real planar mapping, just make those your coordinates. No i's here. This is a real function of a real variable, or two-dimensional output with two-dimensional real input. Don't write any i's if you don't do that kind of thing for part B. And then verify the Cauchy Riemann equations hold for U and V. If they don't, you can't find any mistake. Just say I made a mistake somewhere, you can't find it. Okay. Or say just something shorter. You could say something's wrong. Acknowledge when something's wrong. I don't tell it to students as much as I should. I have told some students more personally that when something's wrong, you know it's wrong on a test, and you just don't have the time to fix it. Writing, I know something's wrong, can often get you like an extra point. For me, at least. To know something's wrong and not pretend that it's not. Of course, there have been a few times where somebody said, I know something's wrong, and they were actually right. That's happened a couple of times over my 20 years here at Bethel. Just a couple. All right, there's this one. I kind of like this one. It's not a guarantee it's going to be on the test, but I do kind of like these problems. This is our first real application of complex numbers. This kind of antiderivative. Other real applications included what we've done recently with improper integrals. And the other main kind of real application we've highlighted has been harmonic functions and Laplace equations, which has lots of applications in physics. It's best to try to expand the function first before doing the integral, so you don't have to write a bunch of integral signs. How? Well, cosine of theta, use the exponential form, is e to the I theta plus e to the negative I theta over 2. Raise that to the 5th power. There's where you use the binomial theorem. And after you expand it with the binomial theorem, you will get things like an e to the 3i theta term, for example, and you'll also get another term with an e to the negative 3i theta. Let's ignore the 1 over 32 here. What would the coefficient be of that particular term? It would come from raising this one to the 4th, this one to the 1st, and also with Pascal's triangle. Let's see, what row would it be? The coefficient would be 5. I guess I better write it down to let's say. Yeah, that's the row with raising to the 5th power. There's your coefficient. So you're going to get one of these here and another one there. That can be rewritten in terms of cosine as well. If you don't see how to do it, well, okay, you can do it this way. Do a little bit of algebraic trickery. Rewrite it like that. One of them, I guess, okay, yeah. I'm just talking about, no, I'm talking about combining. Factoring out the 5 first. And getting 5 times this thing, and then putting 2's here and here, and this would be the same as cos 3 theta. That's really simple. Don't forget, if I had to do the sine instead, don't forget that sine theta can be written in exponential form in a slightly different way. You got to do it this way. I guess I mentioned that. I think you didn't need that in this example. I put it there anyway, just in case you need it. Here was one where we were trying to figure out the area of the image of the set using some multivariable calculus. It was actually not that hard to set up. It seems harder looking at it. Basically, you do a double integral over the given disk of the absolute value of the Jacobian of this matrix, which will be determined. So you got to calculate these partial derivatives, take the absolute value, and do a double integral. And the double integral is best done with polar coordinates. So it's a bit of a review of multivariable calculus, and you should be able to do this kind of problem. So in this case, we've got u is x squared minus y squared plus 4x plus 4. V is 2xy plus 4y. The Jacobian determinant, ux vy minus uy vx. What would that be? Ux, the derivative of u with respect to x is 2x plus 4. The derivative of v with respect to y is also 2x plus 4. Is that a coincidence? It's not a coincidence. Cauchy Riemann equation, or what's relevant there to say that's not a coincidence. Minus partial v with respect to y is negative 2y. Partial v with respect to x is positive 2y. That's also not a coincidence. Giving you a Jacobian determinant equal to something that can't be negative, 2x plus 4 quantity squared plus 2y quantity squared. Can't be negative. So its absolute value is itself. And if you expand this out, you get 4x squared plus 16x plus 16 plus 4y squared. And that would be the thing you'd integrate. And if you use polar coordinates in doing the double integral, which you should be able to do, remember that dA is r dr d theta. Also remember that x squared plus y squared is r squared. X is r cos theta. Y is r sine theta. Remembering those things allows you to do the double integral of this over the disk. It's not too bad. It's not too bad to do. So make sure you can do that. Prove that's an open set. That's one of the possible proofs. Though I might modify it if I decide to have you prove a set is open. It might not be a half plane like this is. This is the half plane to the right of the imaginary axis. It could be. Or it could be, say, the half plane above the real axis or below. Or I might have you prove that an open disk is open. And that was an example I did in class. So if you look back in the lectures, look for the lecture about, I think part of the title says open disks are open, meaning they're open sets. I don't remember which lecture it was offhand, maybe lecture 7 or 8 or something like that. Just a guess. Another proof here, a limit proof. If I give you this kind of proof, it'll be probably a quadratic function. It'll probably even be z squared, but I'll just change what z is approaching. I'll give you one like this, so review that as well. And we did an example like that in class 2. starting the proof with let epsilon greater than 0 be given. And that was the last problem on exam 1. On to exam 2. I need to go faster here now. Things always take longer than you hope they're going to take. Evaluate the values of these things. Capital G, that's the principal value of the logarithm. Look up the formula for the principal value of the logarithm. It does involve a real logarithm for the real part and an argument for the imaginary part. Capital ARG for the principal value, and that argument, remember, is going to be between negative pi and positive pi. I could modify this and put another branch of the multi-valued logarithm function. I could label it something like this. L sub, oh, I don't know, 2 pi of square root of 3 plus I. The argument of the answer would have to be between 2 pi and 4 pi. If I put a sub 2 pi there. Remember, that's how you pick the branch. That also happened with the argument function. Arg sub tau of z. Picking this tau to be 2 pi or something else. This had to be a value between tau and tau plus 2 pi, including tau but not including tau plus 2 pi. That would be that half open interval. That notation then. And it's a similar notation for the logarithm. Principal value of 1 plus I to the I. Remember, complex exponentials in general are defined as z to the alpha. By definition is e to the alpha times log z. So this is a multi-value function in general. But I'm after the principal value, because that's what I said. Therefore, you use the capital log. We get one value. These are problems people had perhaps more trouble on than you should, you might say. Sine of 1 plus I, and next one is cosine of 2i. In those situations, it's best to use the exponential form of the trig functions. For example, sine of 1 plus I is e to the I times 1 plus I minus e to the negative I times 1 plus I over 2i. Then expand this out, use Euler's formula ultimately to get it in terms of real and imaginary parts. This becomes e to the negative 1 plus I. This becomes e to the positive 1 minus I. And for example, e to the positive 1 minus I is the same as e to the first times e to the I, which would be the same as e to the first times cosine of 1 plus I e to the first times sine of 1. I'm writing e to the first, but of course that equals e, so you could just write an e. Do that for this kind of thing too. Simplify. You can write the answers oftentimes in terms of hyperbolic functions as well. Not that they have to be written that way, but they can be. Cosh of z is e to the z plus e to the negative z over 2. There's no i's in that formula, same for sinh. Turns out in these kinds of problems, you can write them in terms of Cauchy and sinh, but you don't have to. Here's the amplitwist problem. And in fact, in this problem, on the next page, I gave you a formula that you really could have used on the previous page. You could have gone back and use this formula that sine of x plus iy is written in terms of sine, cosine, sinh, and cosh in this way. Where we're trying to understand how f as a mapping dilates and twists small vectors that emanate from this point, approximate your dilation and rotation to a certain number of decimal places. It's based on the amplitwist concept, thinking of the derivative as an amplitwist, meaning locally speaking, it takes vectors emanating from a given point and rotates them and amplifies them by the same amount, approximately, when those vectors are small. And the amplification factor is the modulus of the derivative at the point. That can be less than 1, so the amplification can actually be a shrinking. This is like 0.1 or something, and you're shrinking them by a factor of 10. And the twist amount, or rotation amount, can be thought of as an argument of the derivative at the given point. Z0 here is the given point, pi over 6 plus 3i. And I pick that point because it makes the numbers come out not too bad. Of course, and sine pi over 6 can be evaluated. Here you're verifying the Laplace equation. I'll leave that to you. It's not too hard. Here you're breaking up a rational function in terms of partial fractions and calculating the residues. Or, let's see, is that what they're doing here? Well, once you've got this partial fraction expansion of this rational function here, the residue of this function at negative 5i, which is a pole, will be just whatever b is. This will be the negative 1 power of z plus 5i in the Laurent expansion of this function about negative 5i. It will include some positive powers of z plus 5i as well that come from this form. But that will be the power of the negative power of z plus 5i. So the residue is going to be whatever b is. And coming forward to what we've done since exam 3, you should also be able to use this general formula. Residue of a pole of order m, pole at z0, can be calculated as a limit. Z goes to z0 of 1 over m minus 1 factorial times the m minus first derivative of z minus z0 to the mth power times the function that's got the pole of order m at z0. That's the general formula. This formula is a bit of a pain to use if m is bigger than 2. It becomes kind of a pain, like if m is 3, because you have to take a second derivative of this thing. By the way, before you take the derivative, this product should be simplified by cancellation as much as you can. But you'd have to take a second derivative. It could be a big mess. When m is 0 or 1, it's not too bad. You should be able to verify the answer to this problem with this formula as well. It's a simple pole here, which means m is 1. And when m is 1, this derivative is not really a derivative. The 0th derivative doesn't do anything to the function. It gives you the function itself. Integrating with a parameterization, you should be able to do that. You should also be able to integrate with an antiderivative when the function is analytic on the given simply connected domain. Actually, if you've got an analytic function that's got an antiderivative over the entire domain, even if it's not simply connected, you can still use this. You know, things like 1 over z squared are not analytic on the plane. In fact, the domain of analyticity is the punctured plane, which is not simply connected. But this does have an antiderivative over the entire plane. That is an antiderivative of it over the entire plane. And that would be negative 1 over z. Yeah. And that's true. That's an antiderivative of this function over the entire plane, take away the origin. That's what I meant to say. I didn't quite say that 30 seconds ago. Which is not simply connected, but that domain where this is valid is that entire plane, take away the origin. And so you can use the fundamental theorem of calculus in that situation. The problem with integrating 1 over z and not getting 0 is its antiderivative is a logarithm, and it's not an antiderivative over the entire plane, take away just the origin. It's an antiderivative over a slit domain where you take away, for example, the negative real axis. So you can't apply the fundamental theorem of calculus over such a thing if you're integrating, say, around a circle centered at the origin for 1 over z. Cauchy Riemann equations in polar coordinates for this one. First, you got to write u and v in terms of r and theta. People had more trouble with this part A, than I expected. Just expand this. R squared cos 2 theta for the real part, R squared sine 2 theta for the imaginary part. Find a harmonic function. It was just a matter of solving for a and b based on given conditions. Proving that a partial of u with respect to y, where u is analytic, or u is harmonic, is also harmonic. This could be proved as well in your exam, or slightly modified. True-false questions that I might include, may or may not include, maybe with modifications, maybe not with modifications. On to exam 3, another parameterization problem. And also using the fundamental theorem of calculus. There were a few of you who had trouble with this one still. And mostly the trouble stemmed from parameterizing the line. The simplest parameterization of this line segment is that, right there, as t goes from 0 to 1. There's a use of the ratio test. I think most of you got this one okay. Here you're maximizing this harmonic function along a boundary of a disk using the parameterization. It's just a matter of plugging the parameterization in, taking its derivative with respect to t, setting the derivative equal to 0 to find the critical points, and figuring out which ones give you the max value. Some true false. I'll let you think about the Cauchy integral formula for these two things. The Cauchy integral formula says the nth derivative of f at a point in where f is analytic can be found as n factorial over 2 pi I times the integral of f of z over z minus z0 to the n plus first power, where gamma is some positively oriented and simple closed curve around z0 and in the domain where f is analytic. And you can use this formula to evaluate integrals if you divide both sides by n factorial and multiply both sides by 2 pi I. And we typically apply this in the case where n was 0 or 1, when, again, when n is 0, that's the 0th derivative, which means it's the function itself. 0 factorial is 1, you'd get a 1 there. That's the ordinary Cauchy integral formula. This is the generalized one. You need the generalized one for the second one. That's the square here. This one was a proof of Liouville's theorem, and I basically told you what to do, but there were very few of you who got full credit on this one. I did want you to mention the chain rule if needed when you to verify this is analytic over the whole plane based on the assumption that f of z is, and the fact that e to the z is analytic, and really I times z is analytic as well. I wanted those things to be mentioned. You don't actually have to take the derivative, though you could, but it's not really necessary. Find Taylor series and the Laurent series. Actually, use Taylor series to help you find the Laurent series with this one. Most of you got this one. Most of you had trouble, though, on this one. I don't have time to talk or remind you what to do. Too low on time here. Practice it, okay? I think I'm probably going to give you one like this, partially because I want you to get it, okay? And there are about half of you who are not getting this one completely, at least. So practice this kind of problem. I'm going to put one, I'm telling you right now, I'm going to put one like this on the final. I want you to get it. If you didn't get it on the exam 3, get it for the final. You've got to practice Taylor series and Laurent expansions. All right, so what's new? The new thing is, like I mentioned, calculating residues and the residue theorem, and applying it to improper integrals. There probably will be at least one problem where you have to use the residue theorem, and perhaps to improper integrals and their principal values. I think I'm going to leave that for you to perhaps watch one of the recent videos. Let me end class with some visualizations that I wanted to get to earlier but never had the time to. I made more Mathematica code to visualize integrals, and I will save this on the wheel. Looks like a lot of code here. I'm going to visualize somehow the integral of z squared with all this code. And here's how you visualize it. I'm saying to think of the integral as the sum like this involving two real line integrals of vector fields, and then also a plus I in there times this one. We've talked about this before. There's your conjugate vector field, so to speak, phi bar. There's your other vector field that's related to phi star. And this code generates output that allows you to think about the values of those line integrals more easily. As this slider moves, the black vectors move around the circle, and helps you see how ultimately the positive and negative contributions to the integrals give you an integral of 0 in this case. Thinking in terms of areas with these curves that correspond to these dot products, you can see that the integral ends up being 0. I also wanted to quickly show you an example where the integral is not 0. I did briefly mention this before. You can also do complex integration in this way, at least, over a domain where the function has an antiderivative over that entire domain, which this example is not such an example. Because if you find the antiderivative of this, you get something that involves logarithms and an arctangent, which are both multivalued functions in general, so we have to take branches of them if we're going to interpret it this way. But it still turns out you can kind of interpret it this way, as I'm going to show you in this picture that I'm going to show you. You can use residues to calculate the integrals, and ultimately, what I'm most interested in here, I think, is the integral, well, over these three parametric curves here. This one is a circle of radius 1 centered at I. This one is a circle of radius 1 centered at 2. This one is a circle of radius 3 centered at the origin. The poles of this function are at I and 2. You can calculate residues with Mathematica. Calculate 2 pi I times those residues and add up those things to ultimately, for example, find the integral of this function over z2. But what I really wanted to do was visualize this in the following way. What are these graphs? These graphs are graphs of the real and imaginary parts of the antiderivative. And you can see it's not a continuous function over the entire plane. It is analytic over a certain kind of simplified domain that corresponds to taking branch cuts of arctangents and logarithms. And let me just end by saying that that interpretation of the integral as a change in the antiderivative can still kind of be used here if you think about taking limits of values as you approach the branch cuts instead of the actual values. And you can calculate, for example, the change in the function as a change in the limiting values here if you go across one of these branch cuts. I don't have time to explain it any more than that because we're already a little bit over time. If you're interested, I would encourage you to explore more. Okay? See you next Thursday at 2:30.